newest colleagues. So Roshi Nateghi, did I say that right? Thank you, is joining us after, wow, being in so many impressive places. We have AAAS Fellowship, Department of Energy, Purdue University, Johns Hopkins, Imperial College London. Ooh, all right, really incredible. Thinking about and working a lot on power and environmental engineering and thinking about how we sort of navigate the future of electricity. So I won't say much more, but I'm so happy to have you here. Thank you so much.
Thank you so much. Appreciate it. So welcome to the last episode of the seminar series. I'm well aware of the stereotype of engineers, so I'll do my best not to live up to the stereotype and try to be light and as engaging as I can. But anytime you feel like I'm triggering the snooze button, holler, and I'll go faster. But yeah, so before getting started, I see many new faces that I hope to be able to have conversations about some of the topics I'm really interested in. If I may, I would like to take a few minutes to tell you a little bit about my background and how I ended up here. So I did my undergraduate studies in mechanical engineering at Imperial College London. And there in my junior year, I took a course in energy systems that really opened my eyes to the impact of fossil fuel-based industry on global climate change. My instructor at the time, who later became my undergrad research advisor, was very into carbon capture and storage, so very McKenzie way of looking at climate change solutions. At any rate, that's when I really decided to pivot, and I knew that my career trajectory needed to be a little bit more socio-environmentally aligned. That brought me to Johns Hopkins University to do my graduate degree in environmental engineering. Well, technically, the department at the time was called Geography and Environmental Engineering. It's now changed to Environmental Health and Engineering. At any rate, while my undergrad degree in mechanical engineering was as traditional as it gets, I'm not your typical environmental engineer. What it means is that I was in their systems group, so leveraging operations research or our techniques like applied math and statistical learning theory to study systems and look at their impacts on the environment. My PhD focused on reliability of coastal electric power distribution systems under hurricanes. And in my last year of PhD, I wrote a proposal on sustainable energy infrastructure planning for a great program that used to exist at NSF called SEAS, Science, Engineering, and Education for Sustainability. And that allowed me to work at a think tank called Resources for the Future, not too far from here. If you guys are not familiar, take a look. They're a great place for, energy policy work. And afterwards, I joined Purdue University, Department of Industrial Engineering. And you might be laughing that this girl keeps hopping from one engineering department to the other, but there's actually a consistent theme. Over there, I was in their OR group, which meant, again, we were using operations research techniques, but because of the environmental implications of my work, I also had a joint appointment with Ecological Science and Engineering Program and Environmental and Ecological Engineering Department. Things were going fairly well until 2020, when I was going up for tenure and I was preparing my impact document. And it occurred to me that while there's a lot of practical applications or implications of my work for policymakers or decision makers, I wasn't able to get their attention the way I wanted. Sure, we were doing press releases based on our articles, and it was catching attention here and there. Through that, we've actually secured a few consulting projects with a few industry partners, but I wasn't able to get the attention of the larger stakeholders. So I did a little bit of Google search, and for my sabbatical, I did something maybe a little less conventional. So I did the AAAS Science, Technology, and Policy Fellowship, which, again, if you're not familiar with, I highly recommend you look into it, and I'm happy to talk to you about it if anybody is curious, because they work people who are fresh out of school all the way to mid-career and late career. And then I joined the Department of Energy, the Office of Energy Efficiency and Renewable Energy, which is currently heavily dinged under the current administration. But at the time, if you recall, about 80 billion of IRA money flowed to the Department of Energy, and a big chunk of it went to renewables. So things were okay at the time. And halfway through my fellowship, I crossed paths with the Deputy Assistant Secretary of the Office of Electricity. And I realized they were looking for somebody to look at their grid internal strategy document of grid resilience, and that seemed like a dream come true. So I extended my research leave at Purdue, and later I resigned to become a full-time program manager at the Department of Energy. So I tried to start a program for applying methods of risk science to the reliability of the grid, but I also worked on the internal resilience strategy document, which I'll talk about a little bit later during this talk. And that brings me to here. I'm extremely honored and excited to join this vibrant community of scholars and students, and really look forward to the opportunity to talk more at length with you and hopefully start collaborations, discussions, and all sorts of good things. What I want to convey is that on paper, I might come across as an engineer, but the way I view myself is an interdisciplinarian with more in-depth training in engineering infrastructure, data science, and risk science, and a lot of curiosity to work with and drive to work with colleagues in climate science, behavioral and decision sciences. And I hope through conversations with many of you, the petals of this flower just keep expanding so that we can address the fundamental challenges related to the resilience of the built environment, which is what I care most about. So I'm basically driven to address challenges related to the resilience of the built environment. And you might be asking why, and what keeps me up at night is actually, I don't know, sorry if the graphs are a little small. Can you see very well? This is NOAA's data that shows you the cost associated with billion-dollar weather and climate disasters. So for any given event to be recorded in this graph, it should have been costed at least $1 billion or more. And this is, by the way, inflation adjusted. If you look at the black line, I don't have a cursor, but that's the historical average. So on average, you're looking at about like maybe $70 billion of losses. But look at the recent expenditure over the last decade, right? Like we're seeing something almost $400 billion in cost. The costs are staggering. And of course, it's the same story with the frequency of these disasters. Historically, we were looking at maybe $9 billion weather and climate events, but now we are looking at, is it the 2023, we are looking at 28. And you might be asking, Roshi, why are you showing us an outdated graph? Why are you not showing something a little bit more updated related to 2025? And can anybody guess why I'm not doing that? Yeah, because if you wipe out the data, the problem disappears, right? So perhaps that's the strategy. But of course, you might know that this is not just a US problem. Of course, it's very much a global phenomenon. This is a graph by EMDAT, a global repository of disasters. And of course, you know, the sharp uptick is not just increased number and cost associated with disasters. It's a little bit of reporting, improved reporting over time as well, but very much a global phenomenon. And but still, if you look at the most recent reports coming out of EMDAT, you'll see that the US maintains the lead, right? So this is the number of disasters by continents, but they identify the top 10 countries. And of course, we are doing pretty great, both, the opposite of great, both in terms of the number of disasters and the costs associated with them. So perhaps it's not a surprise that I'm extremely motivated to develop risk-informed decision support tools to help communities, infrastructure managers, and operators minimize risks. And when I use the word risk, I recognize like resilience, sustainability, they can be warm and fuzzy, and they can acquire different definitions in different disciplines. So I want to be very clear what I mean by the word risk. Having said that, we have an expert risk analyst, so maybe I should stop and have Robin explain to us what risk is. Robin, shall I carry on, or you want to tell the? If I make any mistakes, please correct me. But anyway, so risk is the way I use the definition of the International Society for Risk Analysis. So the classic paper of Kaplan and Garrick from the 80s, basically you ask three, they call it the triplets, right? The three questions of what can go wrong, how likely is it, what are the consequences over the time frame that you're interested in. So when I talk about risk, basically the risk description is not only a function of hazard scenarios, but consequences and the associated uncertainties not for the only hazard scenarios, but the consequences. The reason I want to be clear about that, because this differs a little bit from, for instance, how our climate scientist friends think about risk, right? If a hurricane develops over the ocean and dies over the ocean and doesn't cause any damage, to me, that's not risk. Or like to an engineer, that's not risk, right? You have to have costed societal losses for it to account for risk. And of course, these type of analyses have been successfully applied in various different industries, all the way from nuclear safety to space aviation. But more recently, we are seeing more complexities, right? There is AI and, going the wrong direction. Okay. Extreme interdependencies in complex adaptive systems. We have climate change. So something that is a conversation that is starting in society, and we are making strides towards, and I'm really interested in this area, is to also communicate the strength of knowledge related to risk and the risk analysis that you're handing in your decision maker. Because you're not always dealing with data-rich systems, that you have differing degrees of confidence related to these risks that you are characterizing, and it's basically a big responsibility to make sure you're communicating those uncertainties or confidences around the estimates that you provide to people. So, so let me give you an example. This is all a little too abstract, so maybe I can give you some examples of the kind of risk-informed emergency preparedness and response decision support tools I've developed in collaboration with industry. So for instance, I've worked with electric utility serving the Gulf Coast of the United States to develop power outage risk models during hurricanes. So what that involves is that you work closely with the engineers at the electric utility, and then you collect all sorts of data, and I'll tell you a little bit about what kind of data goes in there. And then, of course, you work with people in atmospheric sciences to develop your probabilistic models of your hazard scenarios, right? And all of that will go to test and validate a statistical outage forecast model. And then what happens is that if a hurricane is coming close to the service territory of the utility of interest, then you get the estimates of track and intensity from NOAA, run it through your models, and then spit out outage risk maps. And of course, this is an iterative process because you can constantly, engage with the experts and improve your methodology. The interesting thing is that we had cross-validated and tested the models shortly before Hurricane Irene, and we got to run it in real time for Hurricane Irene, Hurricane Sandy, which is why we say this disseminating not only back to the experts at the utility company, but also the community, because at the time we worked with the Maryland Emergency Management System to disseminate some of the results. And actually afterwards, through a DOE grant, we spatially generalized the model, and it's now, I believe, part of the outage risk model that FEMA runs prior to many events. At any rate, I told you about the kind of input variables that might go into your model. Of course, you have to work with the utility to get very detailed information about the topology of the system. Where are the critical assets, substations, primary feeders, transformers, all sorts of interesting stuff, and also really detailed information about the customers, right? The type of customers that you have, their density, and so on. But of course, you need to have information about the topography of the region, the climate of the region, measures of soil moisture, drought, like tree, the tree trimming of the utilities is a big thing during storms, tree covers, the type of trees, land use, and all sorts of things. And of course, your validated statistical model of the hazard of interest, which in this case is hurricane. So as you might imagine, you would have hundreds of covariates of interest or risk factors of interest to parse through. But we use an ensemble of tree predictive methodology to develop an outage forecast, which allows you to parse through a highly dimensional data space and then tell the utility what are the key critical risk factors. So for instance, it can tell the utility that, look, of course, as you might imagine, the customer density, 3-second gust wind speed, durations of winds that blow above 20 meters per second, which is the design load of the electric utility pole. These are the critical factors you want to think about. And by the way, they're not black boxy. You can basically tell your stakeholders what the relationship between each of these risk factors and your outages is. But the beauty of these flexible approaches is that you don't need to be only concerned with one metric of impact, which in this case is number of outages or damaged assets. You can have a multivariate approach to this. So what does it mean? For example, you can do multivariate predictions without compromising your predictive accuracy. So you're still giving fairly accurate risk estimations to the stakeholders, but you're able to tell them what the risks are in function of a range of different impact metrics. For instance, not only the number of outages, but outage durations and the number of customers left without power. So for instance, this heat map tells you that, yeah, of course, customer density and tree trimming are critical across all your metrics, but the intensity of your hazard is more predictive of your outage duration, because this is clustering around here. But then your topography is more predictive of your number of customers left without power. And the beauty of these models is that you don't just run it in real time to help with the preparedness and response decisions of the electric utility. You can also run it in medium term to support investment decisions. For example, we always hear a lot of conversations of like, oh yeah, the hurricane came and the utility had really fallen through with their trimming practices. They didn't do tree trimming as much as they should have done. Or why don't they underground certain parts of their service territory? So you can actually run these simulation box and then see how different scenarios might play out in terms of reducing your impact, right? In this case, there are two hypothetical scenarios. What if I do my tree trimming a little bit more frequently? Or what if I underground certain critical assets in my most vulnerable area? And how does that play out? So if you're a typical utility, and by the way, every utility I've worked with, they're not much interested in other metrics of impact. All they care about is the damaged assets and number of outages. So if that's the criteria of interest, then there's not much difference between the two scenarios I'm running here, hypothetical scenarios. So you might go for the least cost option. But if you do care about the various different impact metrics, for instance, if the customers out is the number of customers without power, the type of customers left without power is of interest to you, you would see that one decision scenarios basically much better than the other. And of course, these are, again, hypothetical because the electric utilities I've been working with have not been interested in this impact metrics. The idea is we can work with communities to build a series of impact metrics that is of interest to the community, and then see what sort of decisions can minimize risk over the timeframes of interest. So of course, I've shown things in the short time and medium time. How about long-term simulation? Of course, we have, So we have these physics-informed statistical simulation box that can tell us how a hurricane will propagate through a power system. But then, of course, if you feed it future climate scenarios and the evolution of the grid, you can get a good sense of how that translates to grid impact metrics. And so these sort of long-term simulations haven't been as much interest to electric utilities. It's been more driven by academic curiosity. But one thing that I've personally found was very interesting in one recent project that we did is that, of course, in collaboration with climate scientists and a colleague in the national lab, what we did, we tried to see, okay, first, how does climate change impact the landfall location, intensity, or frequency of hurricanes? And then how would that propagate through the power systems and end up as outage risks, right? So of course, if you imagine there is uncertainty associated with each layer of these modelings, right? So what I was interested in is, what is my outage risk? What are the uncertainties most sensitive to? And what it turns out is that 95% of the uncertainty in the outage risk model was driven by the uncertainty in the frequency of weaker storms. And this was completely counter to the existing papers in the literature that was done primarily just by engineers who don't consider the physics of hurricane activity. They have, maybe there's like needs probability models of the hurricane activity and you propagate it through your system. And by the way, I'm not saying more intense hurricane doesn't lead to more risk. That is true. But what I'm saying is that if, for instance, if we don't have unlimited resources, if you have limited resources and you want to invest in improving the precision of your work, if our climate scientist friends improve the precision of frequency of hurricanes, that will go a long way in the confidence I'll get around the sort of outage risk estimates that I provide to decision makers. So this is basically maybe providing rationale of why we really need to do truly interdisciplinary research and integrate wisdom from different subdisciplines that are relevant. But in the beginning, I was telling you I'm really interested about the resilience of the built environment, and then I kept talking about risk. So maybe talk a little bit about resilience. And the thing is, as I started doing these long-term projections of power outage risk under climate change, I realized that the way we were having those conversations with electric utilities around resilience perhaps was not resilience. It seemed like us as customers keep subsidizing rebuilding of the same vulnerable systems, right? For instance, one example is, for instance, Florida Power and Light spent billions of dollars a couple of years ago upgrading all of their utility poles from wooden poles to steel and concrete. And of course, the impetus is that it would withstand slightly maybe higher wind speeds or whatever, but it provides maybe an incremental improvement when you do the calculation based on the hurricanes or the storms that you've seen in the past. You're not essentially climate proofing your system, you're making your system incrementally better to something that happens in the past in a way that it's not, I don't know if it makes a whole lot of sense to keep rebuilding the same vulnerable system without upgrading the design codes and doing, or maybe fundamentally thinking differently about resilience. So why do we need to keep, is it about the resilience of the physical infrastructure? Should they just keep existing because they have existed before? Or maybe it's not necessarily about the physical infrastructure, it's about it's about consumers' uninterrupted access to critical services like electricity, water, and whatnot. So then that sent me down the rabbit hole of resilience literature. But one realization is that, of course, the concepts like resilience, sustainability, these are like ingrained in us for thousands of years, right? Like, there are like old proverbs that are pretty great in capturing the essence of resilience. For instance, I mean, I don't read Japanese. I don't know if anybody does, but I think what this one says is that it's a proverb of resilience, and it says, fall down 7 times, get up 8. So the idea is, it's not about avoiding the fall. You will fall, but when you do fall, how fast or how easily can you get back up? Or, maybe here we say, what doesn't kill you makes you stronger. And the idea is that, yeah, you go to the gym and you tear up some muscles, and then that your muscle hopefully and presumably grow back stronger. So you don't go back to what you were before. Your body transforms. It's a little bit different to what you were before. And of course, a lot of other myths in other cultures, like phoenix or Seymour. These are mythical birds that, they catch fire but rise up from the ashes even stronger than before. And I think this is a fundamental essence of resilience that gets lost in the way us engineers think, measure, and conceptualize resilience. The element of transformation a lot of times gets lost. And a lot of times we have a very, here we go, homostatic view of the world. So we expect a system X, there is some disturbance, there's a state of disorder Y, and you expect things to go back to as it were before. Whereas in real life, the reality is that there's always a new order, a new norm that you adapt to. And this is maybe the element that we get sometimes, well, oftentimes blindsided. And by the way, this observation is not my observation, going back to these idioms to correlate. I'm borrowing a lot of ideas from ecology, which I think us engineers have a lot to learn from. So if you sit through any resilience talk of an engineer, They will show you resilience triangle, or if they're fancy, resilience trapezoid. I refuse to draw a triangle or trapezoid because real life is messy. So basically, it's the shaded green area that you see. So imagine that blue hurricane happening in your system, and then there is the black line, the black curve. Your system goes down in functionality, and hopefully at some point, you start your recovery process and you recover back up. And presumably, if you then move from the black curve to the green curve, then as an engineer, I can integrate under the area, you can characterize the area under the curve and tell you the improved resilience. But the problem that I have with this approach is the overemphasis on recovery. I mean, I can tell you the number of times I've sat through presentations by the Army Corps of Engineers that use the words resilience and recovery interchangeably. And it is an important pillar of resilience, but it's not the entire story. The main thing, my main issue is that you don't stop tracking or thinking about your resilience shortly after a hurricane dissipates or another hazard of interest. This is a long game, right? You need to track your system longer down the road. And so, of course, the story that shouldn't get truncated the way it was. And also the infatuation of your functionality going back to exactly where it was before. As you see, the black straight line. Like that is the classic, basically curve that you see in engineering textbooks. But a lot of times it doesn't even make sense to go back to before. I mean, you'd hear from utility companies in Louisiana post-hurricane Katrina, like they had lost a lot of their customer base. Why should you go back to what it was before, right? Like things change. Remember the idea of like allostatic view adapting to the new world, to the new norm. And if you look at we have a curve I, which is going back to before, and then you have the second line, the green line that, of course, your resilience goes up, and then the yellow line, which we consider as resilience trap, which is, for instance, I don't want to be too hard, and please, this is off the record, don't quote me, like I don't want to be too hard on Florida Power and Light, but I suspect that's the kind of scenario that we see where in your adaptation phase, you see a little bit of uptick, like a little bit of improved hazard impact, but in the long run, considering the fact that the number and intensity of hurricanes are increasing, perhaps you're not as resilient as you thought, because maybe that false sense of security is encouraging more development in at-risk areas and so on. So the whole idea is that transformation is a key element of resilience that needs to be considered. And you do actually, if you have a short view of resilience, you can have policies that entrench resilience traps. And so this is very abstract. We've done a case study just to show what it means if you just laser focus on recovery. So we did just a very simple case study, and right now we are collecting more data to, of course, expand the study. But it was only for Hurricane Michael in 2018 in Florida. And basically what we were showing is that if you only focus on recovery when you're doing your resilience and you lose sight of transformation, you might actually leave some communities worse off. And some of the ideas from the paper were actually distilled in an opinion piece that was picked up by the Day One project. So I don't know if you guys are familiar with this. It's a policy incubator, and they were soliciting the science and technology ideas for the first 100 days of Biden administration. At any rate, so we, just to tell you briefly what that study showed is that the schematic that you see on top basically is the result of just running outage risk model that only focuses on recovery, right? And you identify your key risk factors and you see which ones are positively or negatively associated with your recovery. And then the next step is we built an algorithm called contrastive community network that it would look at the entire risk portfolio of each community and then cluster communities based on their similarities in their portfolio of risk factors, right? And then you would say, for each of these risk factors, is there a threshold? If I perturb it, is there a threshold where the community can tip into an alternate state, where maybe you're worse off and you're a community that can become more resilient as a function of that perturbation? And what we found, which was really interesting, is that actually almost half of the key risk factors or predictors of recovery led to resilience traps, in the sense that they were not conducive to generating transformation in the community to enable them to come up in a better resilient state. So basically, the idea is that the key ideas, I guess, so far that I've talked about is that when we think about resilience of infrastructure, again, it has to be a more human-centric or consumer-centric solution, and transformation is a key element of resilience. And I presented some of these ideas when I was in the Office of Electricity, and to my surprise, they were really well received, both the transformation and the consumer-centric part of the conceptualization. And interestingly, at the time, I think if you were following the news, there was, as I mentioned, a lot of IRA money went to the Department of Energy, and then they generated this huge program around grid resilience. I think it was of the order of $10 billion. And they were handing out a lot of grants for grid resilience measurement. But unfortunately, most of the measurements were characterizing the reliability of the grid and had nothing to do with the resilience. And to my surprise, everybody was aware and they agreed with it, but they didn't know what the alternative was, because they had to do something. So I worked pretty closely with colleagues at the Office of Electricity and then the DOE appointed Electricity Advisory Committee to work on a document called the Frontiers of Grid Resilience. And then through that document, we were talking not only about the phases of resilience and how it's a long game, you have to look further down your timeline, and transformation is a key element. We were also identifying the key pillars of resilience and how you can translate that to tangible metrics to track and enhance the resilience of the grid. And the idea was to first publish the resilience document, and then we were supposed to hold a workshop with industry partners and populate this metric, and then publish it for use. And then January happened, and everything got stalled, and that document is probably collecting dust in some corner. And of course, the workshop didn't happen. It doesn't mean that I'm going to lose hope. I'm sure we can pick up the conversations a little bit later down the line, and at least I'm trying to distill some of those ideas in a paper. And now, any questions so far before I switch gears a little bit? All right, but I think this doesn't want to switch gear. All right. So the next part that I want to briefly tell you a little bit about electricity, water demand forecasting under climate change that I've been involved in. And this really started when I got asked to be a co-author of the Indiana Climate Change Impact Assessment. And my job was to tell the group what the climate sensitivity or weather sensitivity of your demand for electricity was in regular climate and under climate change. And as I started to parse through the literature to get started, I found lots of evidence that we are really, really underestimating the climate sensitivity of demand for electricity and water. So just to tell you a few examples of why that is the case. So for instance, if you look at the literature, the assumption is that the temperature sensitivity of demand for critical services like electricity and water is symmetric, meaning so they just use the central tendency of the demand distribution, but through a very simple quantile regression, we showed, so for instance, what you see here is the data, electricity consumption data from PG&E in California, and the red curve is the dry bulb temperature, and the blue curve is the wet bulb temperature. And what you see is that the higher intensity demand is actually more temperature sensitive, which is not good news, right? So when you're experiencing heat wave, just a little bit increasing your temperature might actually tip your grid into instability, right? And of course, this gets a lot more exaggerated under climate change. So if you don't care about the higher temperature sensitivity of your high intensity use, you might actually underestimate the high intensity demand by as much as 40%. And by the way, I'm not showing the most hyperbolic result. We've done it for various different utilities. San Diego Gas and Electric looked, I don't want to say worse, but like more exaggerated than this. Yes, so that's one of the reasons. The other piece was that since 70s, for unknown reasons to me, all the models around predicting electricity demand under different climates, and well, even regular climate, is based on cooling degree days and heating degree days calculated, which is based on surface temperature. And there is not as much consideration of humidity. And we did this study at a national scale, and we show that basically, I think for almost 36 of the states, you get much better predictive accuracy if you consider humidity. And by the way, if you ignore the role of humidity in modulating your demand for electricity, you can actually underestimate the climate sensitivity of your demand in key states like California, Texas, Florida, and New York by as much as 10 to 15%. Another piece, of course, I don't want to show you too many things, but basically due to a host of reasons, like we did one work where we were including the electricity water nexus and found better predictive accuracy. So if you are not accounting for interdependencies in your critical services, if you ignore non-linearities, if you have all these sort of funky assumptions that we don't need to have anymore because we have access to these great methodologies that can parse through your data and give you pretty accurate estimate, you're underestimating the climate sensitivity of your demand, and things get worse under climate change. If we can go to the next slide. Yes. So of course, for all of these work, we've also done projections under various different climate change scenarios. And you see that whatever you're underestimating now will just get much exaggerated under climate change. Now, in one of the studies that we did, I think it might have been the climatic change one, managing the electricity water demand nexus in a warming climate, the one comment that we got was that this is nice and this is neat, but who cares? I mean, a single electric utility wouldn't care as much that far into the future. And if you do it for policymakers, these are computationally really intensive. Who's going to run, downscale GCM models to do this? This doesn't scale. And then we come across to this really interesting paper. Are you guys familiar with climate analogs? I wasn't until I saw this paper, which came out in 2019 in Nature. And the idea is basically you identify locations that right now are experiencing statistically similar climate to your site of interest under climate change. For instance, under RCP 4.5, Washington, D.C. is going to be similar to Paragould, Arkansas by 2080. I've never been to Paragould, Arkansas, but I feel like last summer felt like Arkansas weather. But anyways, and under RCP 8.5, Washington, D.C. is going to be similar to Greenwood, Mississippi. So then we got the climate analogs from this paper and combined it with our statistical prediction models of energy and water demand, and basically try to do the projections using the simplified approach, which is really, really easy and fast to run, right? We didn't need to do downscaled GCM model runs anymore. And there was some really interesting stuff that we found. For instance, only the climate sensitive part of your demand for electricity and water, for instance, is going to grow quite substantially in the Midwest. The climate sensitive portion of your electricity is going to go up in the Northeast, but not as much for water. But the part that was interesting to us was that the estimates that we had under this methodology was actually within the confidence interval of the work that we've done with downscale GCMs. So these are fairly accurate and they're fairly practical. So I guess the message is we have the techniques, we have the capabilities, we just need to get the attention of our policymakers and decision makers. And actually, I'm going to briefly show you 3 more projects. This one was in anticipation of Brian's questions. I know you're interested in nature-based solutions, and I was just trying to think of one of the work that we've done where there is, you're asking about how the nature can modulate some of these extremes. As you might imagine, median household income is correlated with a canopy cover in most parts. This graph alone is for Chicago, which is pretty evident there, but I'm sure that's true in many other parts of the US. And so we worked with really detailed data from ComEd. And so what we did for this study, so this is focused on electricity use during extreme heats of the summer. And we subdivided the customers based on those who are below the poverty line using the 2018 guidelines of, I think it was like $25,000 for a household of 4. So whether or not you're below the poverty line or above the poverty line, interestingly, actually the fraction of people below the poverty line in Chicago is above the national average. So the red border grid cells that you see, so on basically the map on the left is enhanced vegetation index, which I think you, Taylor, can tell us exactly what it is. I've actually worked with your friends or collaborator Brady.
Oh, yeah.
Yeah. So yeah, maybe. That's right. So we have the ABI, and then on the right-hand side, you see the median income. And something that I thought was very cool. So look at how your electricity demand is related to your ABI. So which Taylor will tell us. I don't want to butcher what exactly it shows us. So it shows.
It's how much vegetation is there. It's like NDVI, if you know NDVI, but better. It's a better version of NDVI. Is what they tell you it is.
Yeah, so the better version of NDVI on the x-axis, and then the electricity demand. And the graph that you see on the left-hand side is for below poverty line on a hot day. So BHs, because we did it for heat extremes and then regular days. And then the one you see on the right-hand side is above the poverty threshold on a hot day. And you clearly see that when you have access to ecosystem services like the greenery, it actually modulates some of your electricity use. And so shifting gears again a little bit, another question that we've more recently started asking is sort of the nexus of sustainability, maybe, and resilience. So when a disaster happens and government provides subsidies for people to build back, we are hardly presented the opportunity to upgrade the efficiency of your appliances, right? And to me, something that is really interesting is that, before I went to the DOE, at the bottom of every of my papers, I would write, this has practical implications for the policymakers, and the policymakers should do X, Y, and Z, not realizing that people in different agencies don't necessarily talk to each other all the time, right? Like even FEMA doesn't necessarily talk to the emergency response, the CSER office at DOE. And actually this study got started when I was a AAAS fellow at EERE, and I was in the building technology office. So we were doing a lot of building level simulation models of internal electricity use, and a lot of emphasis during Biden about upgrading the efficiency of your appliances. And then we realized that, what if customers have an incentive to, when they rebuild after a disaster, to upgrade the efficiency of their appliances? So this framework, it took some time to bring together different modeling platforms. So of course we have a hydrologist who gives us a flood modeling risk. And then, of course, we did a really granular building level electricity use. And of course, there was a decision-making module. And we brought all of these together for Harris County for now. Hopefully this gets extended too, to understand whether or not there's an opportunity there. And the preliminary results so far suggest that absolutely, you really can reduce your total consumption for electricity and gas if you're presented this opportunity. And you might actually say, Roshi, I see the improvements of the order of only 2 to 3%. Who cares? Well, actually, even the 2.5% would translate to 1/3 of the electricity use of the residential sector in DC and 3 times the emission. So it does matter. It's not nothing. And I think there is real opportunity in perhaps providing evidence such that there are real opportunities of, looking at the efficiency, sustainability, and resilience together, and hopefully provide those evidence to our decision makers. And lastly, I wanted to show one other interesting work that has recently started with collaborators at the University of Maryland with Allison. You were curious, so as I mentioned, so far I've explained my interest in customers' uninterrupted access to electricity and water. I'm doing a little bit work on mobility. I've done a little bit work around electric vehicles as well. But here we are looking at prolonged school outages after hurricanes. Of course, schools provide education, but also they're critical for the mental health of our students. For some families, it's actually food security too. And it turns out that, of course, many disasters, including hurricanes, are a problem. Over the past decade, I think over 13 million students were impacted by prolonged school closures for hurricanes alone. So we are basically trying to predict the risk of prolonged school closures under hurricane and how that risk is projected in the future. So how is climate change modulating the likelihood of these hurricane-induced school closures, and basically what are the intervention mechanisms in terms of school investments and whatnot that you can do to minimize those risks. So with that, I'll close. I appreciate your attention. And sorry, I hopped from one project to the other. I just wanted to give you as big of a picture as I could, so hopefully start many conversations on these topics. Thank you.
I have a really simple question. So I think on the resilience of the grid, it sounds like a lot of it is about transmission more than more than generation of power. And it seems like burying the power lines just one thing would go a long way for improving resilience. So I just wonder if you can say, is that impression right? And if so, are there things that are getting in the way of moving in that direction?
Yeah, so it's not a simple question. It can actually provide really heated conversations if we have industry partners in the room. So you're right. So the transmission of the electricity. So of course you have high voltage transmission, and then the distribution where we get our power from, right? So it's the distribution side of the grid that is most vulnerable to these high wind events. The transmission grid has higher level of resilience, but you're right that generation is most resilient because of its design code, right? And then, transmission lines are a little bit better, but not as much. And then the distribution grid is absolutely vulnerable. And in many of the simulation work that we've done, undergrounding certain, vulnerable assets can really go a long way. I think utilities usually push back because then the regular maintenance would be more costly because access would be harder. And then usually the biggest barrier that you hear is costs. But the problem is I was working on a project when I was at Resources for the Future, and the big impediment of running a scenario analysis to convince the decision makers is the cost. There is no credible cost of, the real cost of 1 hour outage, 2 hours outage, right, from the customer's perspective, because you want the indirect cost as well. You don't want just the direct damage to the electric utility. But so based on the simulation work that I've done, it's true that when you underground when you identify a few critical assets and then you underground them, you rerun your simulation, of course, you're not impacted as much. But this is something that some electric utility, there's been a lot of progress in certain regions that there's conversations, and it's a big equity issue as well. If you notice, mostly under urban areas, in the downtown areas are undergrounded, right? And then the rural areas are like super vulnerable. But yeah, that I think it's a very complex conversation with industry partners.
I'm wondering about the source of the energy and how that might influence the risk or the resilience of the considerations that you raised, whether it's coal or hydropower or renewables. Is that something you've sort of put into your models?
Yeah, that's also a really interesting question, and I think it merits a long conversation because I think we can get reductive with the answer. So the fossil fuel lovers always talk about fossil-based energy as the most resilient. But it's not. I mean, okay, so let me not inject my own opinions. It's dispatchable, it's reliable. But of course, if you don't consider the interdependencies of like how when your wells freeze, then it like propagates through your system or whatnot. And actually, in 2018, under the previous Trump administration, Rick Perry was like, "Oh, we gotta bring resilience to the bulk power system." But what he meant by resilience was fossil fuel-based industry, and everybody started pushing back. All the regional transmission organizations were pushing back. And then, there's always the thing about how renewables are less resilient. But that's the problem that I spent a lot of time talking to colleagues in the Office of Electricity is when we conflate reliability and resilience, that's where we get the story wrong. Because if you look at even for the storm Uri during the, sorry, I'm like blanking, in Texas. If you look at the contingency plans that they had, basically they'd missed something really simple in their estimations of their peak demand. Instead of just doing a very simple back of the envelope calculation that a first-year undergrad student could do, they had said their worst-case scenario was their peak demand back 10 years ago, like in 2011. And then if you look at their contingency plans, it wasn't the wind or solar that fell through, it was their gas-fired sources. But anyway, so like the reliability is the issue, it's not the resilience, but
wouldn't using fossil fuels introduce greater stochasticity or greater uncertainty later on in the amount of storms or the intensity of storms that would actually have a
that's something we don't capture. But to your point, yes. So because it fuels the climate change. So but that's the link. Nobody, I haven't seen.
Seems like demonstrating that quantitatively through these models.
Yeah, no, that's a good point. That's right. And I've seen work where they're trying to, I haven't seen that angle, and I think that's a really interesting one. But I've seen increasing number of work that they try to show how those unreliable renewables are actually contributing to resilience during storms. But yeah, I think that would be great. Sorry, Freya. Sorry, I'm not going in order. I'm like scattered a little bit. Yes, let's go there and then.
I'm going to ask a nature question. I'm intrigued by the gap between recovery and resilience, and also sort of the gap of that conceptually and how that translates to solutions. And I wonder if ever the recommendations that you're making are perhaps there are biodiversity solutions to making up that gap, like grid-based solutions for recovery, but then, for instance, to breed better resilience, are the recommendations ever things like restoring deltas in the south or restoring mangroves, or more like community-based approaches or nature-based solutions that are focused on bridging that gap to resilience?
No, I mean, I worked on one project about the tsunami impact in Japan, and actually what we found is one of the key predictors that was positively associated with resilience was their coastal forests. So when there's data, you can capture those things. And then of course, like through our collaborator, we had access to covariates, talking about also not just nature-based solutions, but community cohesion and how communities come together. For instance, one thing that I failed to mention, and we found in our study, and sorry, it's a little bit irrelevant, but I just remembered that I didn't mention some nuances that get lost. For instance, one of the usually we say disasters happen and marginalized communities are so vulnerable, and then communities of colors are used synonymously with marginalized communities. But in the Florida work that we did, and we saw something similar in the heat wave of Chicago in 1990s, is that, for instance, Hispanic community was faring much better than even some white communities. And it's, again, the things that we miss, right? Like, it's about how communities come together, community cohesion, self-organization, social capital, things that I think engineers are beginning to integrate in their work, but I think we have a lot to do. So both nature-based solutions and human social capital aspects. Infrastructure alone doesn't answer all your questions. Sorry, I think there was, yeah.
I was curious, you read about like data centers being this new sudden input in a grid that's drawing a lot of electricity.
Yeah.
Is sort of the incidence of data centers being this new hip thing
Yes.
detectable at the level that you're looking at? And if that is creating vulnerabilities, and if so, are there like historical
Yeah.
instances where we can look to like an industry coming in and drawing a ton? And what happened, like what was the response back then?
No, that's a great question. So I haven't done any work yet. It's a huge area of concern. And I know my colleagues at the DOE are extremely concerned about that. But if you're interested about that topic, I'm moderating a panel next week. Maybe I can share the link on Wednesday, and it's about that very topic. And we have some experts. So maybe my answer wouldn't be as good as the experts. So maybe I'll forward you the conversation. Is going to be in my court next Wednesday afternoon. Yeah.
So you talk a lot about like working with the utilities. You worked also with governments. I think one area that we haven't talked about is actually working with insurance companies, because they both charge more for the utilities, but they also sue them after the disaster happens. And so it can be big market drivers of
That's right.
change. Have you worked with them at all? And what
No,
was the
no, I
reaction?
have not. But yeah, that's, I mean, the reinsurance companies are becoming a big part of the
whole
equation. It's very spot on. Maybe we'll go here first and then, yeah.
Okay, so I just wanted to share an experience. I live in Montgomery County, Maryland, and Pepco has this program where they come to your house and kind of improve the efficiency of your house. They put light bulbs and all kind of stuff for you. They can give you a voucher if you feel that your refrigerator is too old, and because of what you are saying, they don't want during peak hours to make their grid less reliable. And they even tell you, if this is going to be peak hours, if you unplug your refrigerator or do this or do that, you'll have a preferential rate because of that. My question is, are there any studies about the cost on the consumer as a person? Again, Pepco I think we had a snowstorm and we didn't have power for days. We had to go to an hotel, and that came from our pocket. And I'm thinking, if you have an elderly person who cannot move, which is by himself, and all kinds, are there any study to understand the cost of the consumer? The funny thing is that after the snowstorm, Pepco wanted to build the consumer for the time where we didn't have power. And the community and the consumers actually said no, because that cost us food going to waste and all kind of things. Are there any study?
But that's such a
yeah.
great observation, and I appreciate you sharing. And it goes with the, when I was talking about the undergrounding, the way to motivate structural changes to the current system is to be able to capture the societal cost. So it's not the direct cost to utility, but what it costs to customers. And that's where there's a huge data gap. The problem that I faced in the past is that federal agencies, at least at the time, would not fund work for surveys. This is expensive. And I haven't seen a lot of, that's something that I was trying to do a couple of years back. I haven't revisited, but there's lack of data. And that's that, to your point, if we have the indirect cost of, and I've seen sporadic work here and there, but if we have access to indirect cost of outages, which is a big thing. And to your point, like there's a big difference between the cost of an outage that is 1 hour versus 8 hours versus a week. And I think if we capture that, we can really run a lot of really great resilient solutions.